All right, today we are actually starting chapter 5 officially. So we are going to solve systems by graphing. Those of you that were in a different class last semester may have already done this. So for our warm-up, we are just going to graph both of these on the same plane. That will end up being a lot of what we do today. Graph two lines on the same plane. So for our first line, let's go ahead and identify our M and our B. What's our M for the first line? 2 or 2 over 1. I won't include the X when I write my M's, just the number. What about the B? A 1, or you could call it the 0.01. Let's just go ahead and do all of that first line, and then we'll talk about the second one. So we start our point on the, which axis? Y-axis. Remember, the Y-axis goes up and down. We go to +1, we put a point. Our slope tells us where to go where next? Up to and over which way one? Which way?
You said right.
Oh, right. Very good. Thank you. And then we keep doing that. We get more points. Or instead of going up and right, we could go... Deontay?
Down to left one.
Down to left one. Good. There we go. We should get a straight line that goes through those points. And you will also want it to go through your coordinate plane. I cannot get it lined up there. That's better. Okay, you'll want it to go through like the whole grid. Not just a little bit of it. Through the whole thing. Questions about graphing that first line? Concerns, confusion. All right. Next line. I'll switch colors. What is the slope of my second line? -3 over 1. Nobody's saying it loud and proud. What about the B? Everyone's so quiet. 6. Thank you. You guys know this. You can be a little louder about it. You don't have to whisper. All right, we start our graph on our y-axis at +6. 1, 2, 3, 4, 5, 6. Put a point. 2, 3. Okay. Then we use our slope. This time our slope is negative, so our line should be slanting downhill when we make it. To get more points, I use my slope, and it tells me that I should go...
Down 3, right 1.
Down 3, right 1 is one option. It's a good option. Down 3, right 1, down 3, right 1. Or we could go... Instead of down and right, we can go...
Up 3, left 1.
Up and to the left, so up 3, left 1. The more points you have, the better off you'll be. You're not required to put every possible point on there, but the more points you put, the better your line will end up being. Nice straight line going through almost the whole grid. Questions about the warm-up? Okay, that is almost all of what we do today. The only kind of extra thing that we're adding on at the end is going to be to identify the point where those lines cross each other, which I think most of you could already do right now. But we'll save that for just a minute. Questions about the warm-ups, graphing lines? Warm, fuzzy feelings all around? Okay. Then let's move on. We are talking about systems of equations. We are going to learn 3 different ways to solve systems. I'll tell you that right now. So we're talking about systems a lot this week and next week, maybe even the week after that. A system of linear equations is a set of 2 or more linear equations with the same variables. So for example, 2x plus 3y equals 6 is our first equation. Y equals 4x minus 5 is our second one. The solution of a system of linear equations is an ordered pair, or a coordinate point, that is a solution to both equations in the system. It has to work for both of them at the same time. For example, 1, 3 is the solution to the system of linear equations warm-up problem. So that problem we just did, you can see those lines crossed at the point 1, 3. That would have been the solution to that system. They did not give us a solution to this example system. We could find it. We're not going to right now. Maybe later. Questions about what a system of equations is, what a solution would look like. Need more time on this slide. Then on we go. The solution of a system of linear equations is an ordered pair that is a solution to both equations. We just wrote that. I don't think you have to write it again. So we are asked the question, what does it mean to be a solution to a system? So what it means is that it works for both equations at the same time. So what does it mean? If x and y are plugged in or substituted in, the equation makes a true statement. And that's got to be true for both. It's got to happen for both equations, not just one. Okay, so for it to be a solution, when you plug in x and y, the equation makes a true statement. So for example, they give us this equation, these system of equations, y equals 4x plus 1 and y equals negative x plus 14. They went ahead and gave us a solution of 313. So we can show that that's definitely the solution by taking each equation, y equals 4x plus 1 and y equals negative x plus 14, and plugging in the x's and y's and showing that we get true statements, or seeing if we get true statements. I guess we're trying to check to see if this works. I don't think this is a solution. Okay. On the first part, what am I plugging in for y here? What's the y from my solution? 13 is the y. Remember, ordered pairs go x, comma, y. So I'm plugging in 13 for y. What am I plugging in for x? 3. Why did I put parentheses around it? So that I remember we're multiplying 4 times x, or 4 times 3. Now we need to see if this really makes a true statement. So we are going to simplify the side that has some math to do, which would be the right side. 13, there's nothing to simplify. It stays 13. By order of operations, what do I need to do on the right side first? Multiply. 4 times 3 is 12. Then we add the 1, we get 13. So, did we get a true statement? Yes, we did. Questions? Okay, let's go ahead and check the other one. To be a solution, it's got to work in both equations. And I'm not convinced right now that it's going to work in this one. What am I plugging in for y again? 13 equals, what am I plugging in for x? a 3. So there was a negative x. I'm going to make it a negative 3. Again, 13 doesn't simplify. It stays 13. What is negative 3 plus 14? 11. Did this make a true statement? No, it did not. So that means this is not a solution. It worked in one of them, but if it's going to be a solution, it's got to work in both of them. Questions, concerns? Need more time? Okay. We'll do 2 together, and then I'll give you a minute to try 3. Some of you might have already started on 2. That's fine. Same steps that we just did. We're deciding if this solution they gave us really works. Is it really a solution? So we have to plug it into both equations. Y equals 1/2 x plus 3. And also y equals negative x plus 6. We'll start with the first equation. What am I plugging in for y? A 4. 1/2. I put parentheses instead of where my x was. But what number goes in there? What's plugging in for x, Dominic? The 2. Yep, no, you're right. The 2 goes in for x. We put parentheses so we remember to multiply. We go by our order of operations to simplify. What is half of 2? 1. What is 1 plus 3? Did we get a true statement? Yes, we did. So we can go ahead and check the other one. If your first one gives you a false statement, you don't even really need to bother with the second one. You already know it's not going to work overall. In the second one, what am I plugging in for y? 4 again, same y, same solution. This time I've got a negative x, so I'll write it as a negative 2 plus 6. All right, we simplify. We take negative 2 plus 6, and we get I know more people know this than just Dominic. We'll let him help us out this time, though. Dominic, what is it? 4. Very good. Did we get a true statement? We sure did. So is this a solution? Yes or no?
Yes.
Yes, it is. So this is a solution. You could say yes. You could put is a solution. Something along those lines. Even just a yes would suffice because it said tell whether or not it's an ordered pair or it's a solution. You could just say yes, it's a solution. All right, if you have not already done so, go ahead and try example 3 on your own. We'll talk about whether or not it's a solution in just a moment. Let's see, thumbs up for solution, thumbs down for not a solution, thumbs sideways for you got no idea what we're doing. Lots of thumbs down, that's good. Okay, if we were to try this in the first equation, it would look like it works. 5 equals 5, that works out. But when you move on to the second or bottom equation that they gave us, we would have 5 equals negative 2 times 3 plus 5. We would multiply, doing our order of operations, and then add. And that does not give us a true statement. So no, not a solution. Questions, concerns about example 3? Okay, we'll move on. Couple more for you to try on the back. Some of you may have already done them. That's fine. Just wait patiently. If your partner near you finishes them, you could compare answers. Give you a couple minutes to do these ones. Talk about them in a minute. On example 4, is this a solution? Thumbs up, yes. Thumbs down, no. Thumbs sideways, not sure. Seeing some thumbs up.
Yes.
Any thumbs down? Thumbs sideways. Let's check it out. What's going in for y? A 5. 5 equals 4/3 times. What's going in for x? A 3. All right, 4/3 times 3. That is not that challenging because what happens to the 3's? They cancel out. So we're just left with 4 plus 1, which is 5. That one worked. We try it in the other one. -3 plus 8 is 5. That one worked. So yes, it's a solution. Good job with the thumbs up. Example 5. Thumbs up, thumbs down. Is a solution, is not. I'm seeing mostly thumbs down. Which one did you use that told you it wasn't a solution? Like which equation didn't work out? The first one didn't work out? Okay, so if you find one that doesn't work out, you can stop there. I don't think it would work in either of them, actually, but we just need one of them to fail to show that it's not a solution. This one does not work, so no, it's not a solution. We have questions about deciding whether or not something's a solution to a system. Okay, then we'll move on. Solving a system by graphing. We'll fill in those steps. They're just written with the example, but those steps go in that box in your notes. Step 1, graph each linear equation. So that generally means you'll have 2 of them. Graph them both. Find the intersection of the 2 linear equations. Step 3, very important, write the solution as an ordered pair. An ordered pair, meaning it's written in parentheses with a comma in between. Goes x, comma, y. So those are the steps we're going to follow over and over and over again to do these problems. On example 6, let's start with the top equation. This is in slope-intercept form, which means I can identify my M and my B, just like I did in the warm-ups. What's my M? Careful. -2/1. It's okay. B is 4. You start it on your y-axis. This is the most common error. People want to start it on their x-axis. Don't do it. Start on your y-axis at +4. Put a point. Who can tell me where I could go to get more points? Well, let's make sure that doesn't happen again, or it's going to the office. Then it should be off and in your book bag. Jasha?
Just let them know.
I appreciate you letting them know. Let's get back to our notes. We ready? Where am I going to get more points? Liam. Down 2 and to the right 1 would work. Down 2, right 1. We'll do it several times. Or instead of down and right, we can go
Up 2, left 1.
up 2 and left 1. Okay, we can put our line through those. Remember, nice straight lines through your whole grid. The more points you have, generally the easier these are. We move on to the next one. X equals 2. We did an example of this yesterday. This is one of those special situations.
We just put it we go 2 over on the x-axis and then write a vertical line.
Very good. X equals means we have a vertical line. So we go to 2 on our x-axis, and if you really want to, you could put a little point there. It's not necessary, but you need to know you need a vertical line straight up and down through your whole graph at x equals 2. Questions about graphing either of those? Okay. Then we need to find the intersection. Where do those lines cross each other? If you want, you can make that point a little bit bigger and bolder. You gotta find where your lines cross and then write that as an ordered pair. Lydia, do you have it? 2, 0, I agree. 2, 0 is how we would name that point. Questions about example 6? Need more time on this slide. Okay. Let's work on example 7. Same steps, new lines. This time we are not going to have a vertical line. Both of these lines will be slanted some way, somehow. Let's start with my top line by identifying M and B. What is the slope of that first line? Negative 1 over 1. And B is 2. We start on the y-axis at positive 2. Where do we go from there?
Down 1, right 1.
Down 1, right 1 works.
Or up 1. Nope.
Yep. Up 1, left 1 is the other way we could go. We can get lots and lots and lots of points. You don't necessarily need all of them. The more you have, generally, the better this goes. Make sure your line goes through the whole grid. If we're looking for lines to cross each other and you just make them teeny tiny little lines, you might not be able to see them cross each other in the graph. That's why I keep saying to go through the whole thing. For the second line, what's my slope? Negative 3 or negative 3 over 1. And my B is negative 6. On the y-axis, we go down to negative 6. Put a point. From that point, where can I go?
Down 3, right.
Down 3, right 1, or we could go up 3, left 1. 1, 2, 3. Okay, the more points you put, generally the better your line's going to be. 1, 2, 3. Nice straight line through those points. Next, we're looking for where those lines intersect each other.
I'm not sure if I have my lines correct, like straight, but I got up 6, negative 4.
So I think we can see it here. So I think you're right. But how would we write that point as an ordered pair? Good. Negative 4 comma 6. So I agree it was up 6 and left 4, but as an ordered pair, we put the x, then the y. Questions, concerns? Need more time on that problem? Those of you that have blank graphs are making me think I already need to start calling and emailing home. This is too early to be slacking off. All right, number 8, we step it up a little bit again. The first equation we can go ahead and deal with. It's already in slope-intercept form. That's nice. What's our slope? Negative 1/2. Our b is 1. Always start with your y-intercept. So on the y-axis, we go up to 1, put a point. Then we use our slope. Where are we going?
Down 1, right 2.
Very good. Down 1, right 2. Negative slope. Our line should slant downhill. To get more points, we can go up 1, left 2. All the points. We can put a line through them. Even if you don't put all the points, make sure your line goes through the whole graph. Next, our other line is not in slope-intercept form. So we can't identify m and b until it looks like y equals mx plus b. So off to the side here, I'm going to show my work for putting it in slope-intercept form. We did a few of these in our review yesterday. What do I need to do to get y alone?
Subtract 2y.
Let's leave the 2y where it is.
Subtract the x. 2.
Subtract the x. So we want to get stuff away from the y. So I would recommend subtracting x. If you do it to one side, you better do it to the other side.
Y equals
What's
x plus 2.
Very good. The correct way to write the other side is negative x plus 2.
Divided by negative 2.
Divide everything by 2. All 3 pieces.
Y equals negative 2.
So what fraction could I put in front of x?
1.
Negative 1/2. So there is a 1 that goes right in front of that x. If there's a negative sign, so we treat it like a negative 1. So y equals negative 1/2 x plus 1 when we take 2 divided by 2. Questions about getting it into slope-intercept form? Now that we've done that, we still have to identify m and b, and we have to graph it.
It's the same.
It's the same line. Interesting. So if we graph that line, again, you don't really have to do the whole thing again. But if I were, I'd be tracing over the exact same line. Now, those of you that have seen this, I'm sure you already know the answer. Where do these lines touch each other?
Origin. Nope.
It's kind of a trick question.
People didn't know. Same.
They touch each other at every single point we made, right? They touch each other here, and there, and here. And other points that we didn't make, points in between those points. So if I could pick any point on this line, how many solutions am I going to end up having?
2.
More than that. So let's throw it back to maybe an even more basic situation. If I had an equation that said x equals x, what's a number I could plug in that would make that true?
1.
4. Sure, 4 equals 4. 1 equals 1. Any others? Oh, 1, not a 4. Any other numbers I could plug in that would make that true? 2? 0? Somebody said something that's on the right track here.
Is this one of those special ones? Wait, it could be either all real numbers or infinite solutions.
So in this case, we would say all real numbers. But in this case, we would say infinitely many solutions. There are so many points on that line. There are infinitely many solutions here.
Okay.
Infinitely many solutions. So if you end up with the same exact line both times, you have infinitely many solutions. You will not just write an ordered pair. This is considered a special case. We're almost through next. We're getting close. Okay, questions about 8. I know 8's a little weird. Alrighty then, let's move on. Let's try number 9. I'll give you a heads up. This will also end up being a special case. We'll treat it like normal though, and then see how it turns out. These are in slope-intercept form for us already. That's nice. What's our slope for the top equation? 3 or 3 over 1. What's the b?
2.
Well, we always start with the b on the y-axis. So put a point up at 2 on the y-axis. From there, where will I go?
Up 3. Right.
Up 3 into the right 1. Or I could go down 3 to the left 1. Now I keep hearing the same couple voices responding every time. If you aren't able to say this in your head to yourself without us saying it out loud together first, that might be a problem. Everyone should know how to use slope to get more points. Let's move on to the second line. What is my slope? 3 over 1. What is my b? -5. So this time I'm starting on the y-axis at -5, down 5 from my origin. To get more points, where am I going? Up 3, right 1. It's the same slope, so I'm going the same direction. Up 3, right 1. Up 3, right 1. Up 3, right 1. Or I could go down 3, left 1. Down 3. Oh, Jasha noticed something interesting. Where do they cross each other? They don't. So when we graph these lines, let me see if I can get that line in there. There we go. When we graph these lines, they don't touch each other at all. And they're not going to, even if we continued them on. So there is not a solution. No solution. If the lines don't touch each other ever, there is not a point of intersection defined. Now, some of you may have already noticed this. What was special or true about this problem from the very beginning? What did those lines have in common?
The same slope.
The same slope. Anytime two lines have the same slope but different y-intercepts, so same m but different b's, there will be no solution. They have the same m and the same b, that's when we got infinitely many solutions. Questions? Concerns? Need more time on this slide?